So, we are coming to the second part of the application of definite integral. We have found areas, we will now find volumes. We are not going to tell you the theoretical things, how you should go about it, drawing picture. We will start with an example. From the example, it will be clear to you how to operate. So, you will simply learn how to do the stuff just by visualizing those things. See, here we will study largely from Thomas's calculus. We will take some example from Thomas's calculus, which are worked out by the way, and try to explain them. Okay, because here they do not give too much of explanation. So, here the first problem is that okay, if you have a pyramid, you know what pyramids are, you have seen in photos about Egypt, and if somebody amongst you have gone to Egypt, you are more lucky than me. So, it is like a thing like this. So, its base is actually a square. I am telling you to find volume of the pyramid. Suppose I put stuff inside this, volume of the pyramid whose base is 3 meters, 3 meters. How do you do it? Now, in calculus everything is looked at the point of view of the infinitesimal, that is, you take a look at a very thin part of it, a small part of it, and then try to sum over those small parts. That is the key idea. So, here if you look at it, here is the x axis, the y axis, and there is the z axis, whatever, or whichever axis you want to call. Maybe you would like to call that the y axis. So, this is a 3-dimensional figure. So, what is there is that I have drawn the pyramid like this. I will just try to make the drawing look more authentic. I want to put it on this base. Okay, I will try to draw the square. You draw the square base of the pyramid. So, you draw the square base of the pyramid and add this part. So, the 4 parts, and if this is square base would look like this, and add this part. So, this is what it looks. The pyramid looks like this. So, here at the end is your 3 meter. So, my drawing might be very bad, but so 3 meter, 3 meter, 3 meter. So, what you do, you take the pyramid, it would have been good if I had models to explain you. You basically chop the pyramid up as if you have a slice of cheese and you are chopping it up very finely. So, you are chopping it up. So, one of these chopped up zones you call AX, chopped up zones at a point X, and you want to find the area of this. Right. So, what is the volume? See, all the sectional areas, if I chop up, if I suppose I have the pyramid, I have chopped the head out. Now, in the truncated pyramid that I will see, that is something like this. Whatever. This is actually a square. So, here also what you see is a square. So, square, these are the point x, say it is a square of length x, and the pyramids are done in such a way, their things are done in such a way that if you chop out some x amount, this will be of length x. So, these are of sides x. That is the very structure, the symmetry of the pyramid, that if you have come x from the origin, then the if the base of the pyramid is x, so this is actually 3, right. If the base of the pyramid has x, the sides are x, the square, then the height of the pyramid is x. Basically, if this is 3 meter, then this height is also 3 meter. This is how pyramid is made. So, what you do? You find the area of that cross section. Basically, what happens? If you take all these small cross sections and pull them up and club them, that gives you the volume of the solid, that gives you the solid, and the areas actually contribute to the volume. So, basically what you have to do, this is my A of x, area evaluated at the point x, which is x square. So, the volume is nothing but, so I am summing up all the areas, so which will actually contribute to the volume. So, here we do it in a continuous fashion. So, we integrate from 0 to 3 Ax dx, which is integrating 0 to 3 x square dx, and you can write the answer obviously. Nine cube by 3, which is 9. Okay. Now, let us look at a more interesting example. Take the graph, this root over x. Take this function root over x from 0 to 4, that is what we had studied. So, here f x is equal to root over x. Now, suppose I rotate this, suppose here is my hand and I am rotating it like this. So, in that space it is like if you take this book, do not think of the fat part, just think of this. So, I am rotating this book. So, here it is a rectangle. So, when I am rotating this, just in your mind's eye just see what happens. What does it generate? It generates a solid of revolution. It generates a solid. So, if I have a rectangular region and if I generate it, if I move it in the space, if I rotate it around the x axis, so I am rotating it around the x axis, then for a rectangular zone I generate a cylinder. So, these are called solids of revolution. So, here also if you rotate this one, you will possibly generate an object like this, a part of an egg sort of thing, one end of an egg. So, how do you find its volume? So, once you have rotated around the x axis, basically your whole thing goes in a circular motion. So, if you now cut the slices, if you have a slice here at x, this slice, how do you find the area? Because now it has become a circular slice. It is no longer a square slice that you see here, it has become a circular slice. So, once it has become a circular slice, what are you going to do? What would happen? So, once you have a circular slice, so now this is your x, this is your root x. So, now you have a circular thing of radius root x. Okay. So, basically you will have pi root x square, right. So, area A of x. So, now if you again club up those areas together, you put those areas one after another, they will contribute to the volume and form the volume. So, this is what you have to see in mind's eye, and that is what I have been telling you from the beginning, that is what I believe, and mathematics has got lot about visualization. Without geometry, mathematics does not just progress. Now, if you look at this, what is A of x? Pi of root x whole square, pi r square. So, my volume of this particular solid is integral 0 to 4 pi of x square dx. So, it is pi of x cube by 3 0 to 4. It is pi of 4 cube means 64 by 3. Oh sorry, square root, oh sorry x, pi x, I am making a mistake, right, x square, so x square by 2, thank you. So, it will become square root of x is x, so it is pi of, so it will become what? It will become 4 square 16 by 2, so 8, so it will become 8 of pi. So, you see the area becomes so simple, 8 of pi. So, now if I have a circle and then I rotate it along the x axis, what will be formed? So, I have a circle, now I have a circle, x axis, y axis. So, here is my circle. So, x square plus y square is equal to a square. This is a, in x axis this is minus a. So, if I rotate this in the air, you can think, take a circle object and try to rotate it. Do it in your home, cut out a circle from a paper and just try to rotate it and see what it generates. It will actually generate a sphere. So, this will actually generate a sphere of radius a, whose every cross section is a circle. We can have a cross sections of big circles of radius a, right. So, how do you now, can I use the same method to find the volume of a sphere? You see the same type of ideas we are using to find the volumes, it is the same type of ideas, there is no. So, let us try it out with the circle, with the sphere. So, now we are going to find the volume of a sphere. So, what do I do with the, how do I look at the volume? So, I take any point x. So, here is my sphere, here is my x axis. So, here is my sphere. My drawing is not exact, please forgive me for that. So, here is I have cut out a section at a given point x. But you see, any section that I cut out corresponding to the x, if I hit, so what I cut out? I cut out a circular section. So, this is my x, but then what is my y? So, if I cut out any section, you just take a, just think of that you have a in your hand, orange, and you just cut it off. So, you cut out a section and just cut one part off just with the knife, or if you have apple, you just cut one part off, or just take a orange, that is better. Cut one part off, what do you see? You see the peel and you see the oranges inside. So, if you take any point x, the middle, which is the center of the circular disc, and you just hit the top, what you hit? You hit another circular disc, which is of radius a. So, this point, this height is nothing but root over a square minus x square, because any point on this great circle is of the radius is of the equation x is of the form x root over a square minus x square, because any great circle has the equation x square plus y square is equal to a square, because what is this? What is a sphere? It is a rotation of those great circles. You are rotating that circle in the air. So, at every passing moment you are basically at every time instant you are passing a circle is there in space. So, now what is my Ax?
You use this great circle ordinance, you explain it other than the
So, great circle, if you take a sphere, take a globe, if you have a globe in your home, look at the equator. Equator is a great circle. Just take a path perpendicular to the equator through some of its central points is a great circle. So, take the equator, take the radius of so that is the radius of the earth, right, assuming that the earth is a sphere. So, that is the radius of the earth. Then any circle that lies on the surface of the sphere with the same radius is called a great circle. So, I am sure many of you have heard the terminology and many of you have not heard the terminology. So, but that is it. When you can go and look at the globe at your home and try this thing out. So, the equator is a great circle. So, equator is this one like the earth. So, any circle, for example, this circle, you will draw a circle here or take some circle here. Obviously, you cannot draw a circle here because it will have the curvature, but if you draw a circle, if you cut off like this, if you have a circle like this, then this is not a great circle, but a circle like this one which has the same radius is a great circle. See, what we are trying to say that even if you chop off some part, the y point from that x is always lying on some great circle. So, because ultimately the spheres, the spherical volume is a union of great circles. So, you have one circle which is a great circle and then you are basically the equator, then you are moving it like this, the equatorial plane of the earth, this one, and then you are moving it like this, you are just rotating it around the x axis, right. So, that is what is happening. So, Ax is nothing but pi into root over a square minus x square whole square. So, now volume is integral from minus a to a pi of a square x square, minus a to a pi of a square minus x square. I would like you to calculate this to give the answer pi a cube by 3. You see, so things just by some geometric imagination, simple geometric imagination, you could achieve so much things using the calculus. So, that is what gives me much more joy to think about this subject, that many things like washer method, this, that, so many things, but everything cannot be really figured out in all these classes. Everything need not be done because you still can do something. So, we will now try to look at lengths of parametric curves, right. That is what happens sometimes, given a curve which I have learned at high school, I can bring in. So, what is a curve? Curve means for me some curve line in the xy plane, and usually I would like this to be defined as y equal to f of x. So, but then in many times it is useful, for example, to introduce a third variable t and express y as some h t and x as something phi t. So, then we call this a parametric representation of a curve. So, with respect to t. So, let me now look into find the lengths of curves which have parametric representation. So, examples of curve which have parametric representation. This is very useful. This parametric representation is not only useful for these calculus courses, but is also useful in very advanced mathematics like algebraic geometry. So, for example, if you have a circle, so you know suppose it is x square plus y square equal to 1. I can represent this curve as x equal to cos t plus y equal to sin t. So, you bring in the variable t. So, I basically, so I have x is written as some f of t and y is written as some g of t. I will just go by the notation of this book, so that it's, if somebody uses it, you can obviously understand this. So, x is f t, y is equal to g t. So, this is the parametric representation of a curve. T can be in many cases restricted between b and a, but not necessarily. In this case, t is free, any t that you choose. Of course, you can say, okay, I can represent t, t can be represented from minus pi to plus pi. In this case also, does not matter, it will be the same. So, this is called a parametric representation. Suppose you people have also studied a parabola, y square equal to 4ax. So, x equal to 80 square and y is equal to 280, because you see now if I put y square is equal to 4 a square t square, and if I put 4ax is equal to 80 square is equal to 4 a square t square. So, this is the parametric representation of a parabola. So, this is your ft and this is your gt. So, curves can be represented by parameters. Now, if you can represent a curve by parameters, then it becomes very easy to actually compute the length of these curves. Like any point on this curve, say here, can be represented not by just x y, can be represented as cos t sin t, right. T is actually the basically angle. Now, if you have a curve defined by a parameter like this is a parametric representation. So, how does one find what is the length of this curve? It is actually pretty simple. So, let us see how do we derive the length of this curve, and maybe in the next class we can talk a bit about its applications, not to this but to also next classes basically, which would be in the 7th week of your last about 1 week of your lectures. So, let us now find the length of a parameterized curve. You will see here the beautiful application of mean value theorem. Now, you see if you take any curve which is lying on the plane, and then you can actually approximate it by straight lines, piecewise curves. So, that is why linearity is such a, because our minds are very linear, you know, our minds can't think in terms of curves, our minds always think in terms of straight lines. Suppose you have a curve like this. So, what I do, I actually make a partition of this, say from A to B. Basically, I make several partitions. So, this point I call P0, I will put another point say P1, another point say P2, another point say P3, P4, P5 and so on. So, here I join this point by straight lines, these partitioning points on the curve, and then I get an approximation of the length of the curve, which is not exactly the length. So, you can understand, if I keep on increasing my partition points, some way the length will come. So, let me look into a very small cross section where you have the point P k minus 1 and P k. Okay. What is this point? What is this point? So, what is happening? We are basically now breaking up the interval. So, t is lying in the interval a to b, not x or y, please understand t. So, x and y, so there is no, we are not showing any relation between x and y directly. We are showing, we are telling that x and y is linked, but they are indirectly linked. They are linked essentially with a third variable t. So, it is a third variable on which we will play the game. So, I break it up into sub a is t0 and t1, t2, whatever, the way you do in Riemann integration, tn equal to b. Now, this is tk minus 1, this is tk minus 2, basically those 2 points, right. It is actually y equal to fx, but okay, just take these 2 points. So, this is x and y. So, this point corresponds to the point tk minus 1. So, this is, and this point corresponds to the point tk. So, here my coordinates are f of, so x is x and y, so f of tk minus 1, g of tk minus 1, and here it f of x of tk and g of tk. So, basically I am, instead of looking at this curve, I am looking at the length of this straight line. So, which is nothing but the change in x by change in y. So, the length of this line, which I call say delta L, if you want to call this length of this line as delta L or LK, if I want to call, whatever you want to call, does not matter at all. People have notations, I am not so much worried about notations, still you know the stuff. So, LK, kth piece, basically first piece, second piece, third piece, fourth piece, so on. So, the kth piece. So, length of LK, if you look at it, is nothing but the change in x, this is Pythagoras theorem. So, root over f of this part, f of, so x coordinate, change in x coordinates. So, this is the change in x coordinates. So, f of, this is x coordinates, f of tk minus f of tk minus 1 whole square plus g of tk minus g of tk minus 1 whole square. Now, apply the mean value theorem to this, each of them, fk minus tk minus 1, gk minus gtk minus 1, assuming then f and g are nice functions. So, assume that f is a smooth function, right, and f and g have continuous derivatives in the interior of AB, and assume that f and g are nice functions. So, assume continuity, continuous on AB and has derivatives on AB. Adding a bit fast, we are already over time. So, what does this give me? This give me some t lying between Tk and Tk minus 1, which I do not bother, f dash t star Tk minus Tk minus 1 whole square plus this is also whole square. So, this I can write as delta Tk. So, g dash t double star whole square Tk minus 1 whole square. If I write Tk minus whole square as delta k, then Lk is nothing but root over f dash t dash whole square plus g dash t dash whole square into delta Tk. Now, what is T dash? It is lying between Tk and Tk minus 1. And what is T double star? T double dash here, T double star. What is T double star? It is also lying between Tk and Tk minus 1. These are just tags. So, this is a function value you are integrating over. So, you are actually, if you sum them, if you sum the Lk, so you get the length of the piecewise curve, piecewise straight line, right? The curve formed by the piecewise straight lines. But that length will come more and more near to the length of the actual curve as you go in tending to infinity. So, these T star or T double star are nothing but tags on the interval delta Tk, right. As k goes towards infinity, then the position of the difference between T and T star and T double star in every interval will actually come down. So, basically they will come to a tag point. So, if you look at it as n tends to infinity, the length of the curve, so this is now integration where this is the function of t, right. This is nothing with two tag points, does not matter. I have two different curves I have written in terms of two different tag points. Ultimately, when they will become smaller and smaller, the tag points will be coming nearer and nearer, and so ultimately what you will get. So, this is nothing but length of the curve is integral a to b root over f dash t whole square plus g dash t whole square dt. That is exactly the length, and how we will apply to find this the plane curves would be our discussion. We will start with the circumference of a circle, finding it for some other curves, maybe you can try for parabola, whatever you want. So, we will use some of them in our next lecture. So, our 6th week ends here and 7th week will start, which will have two more classes of these things and then applications, and then we go into more involved series. We are now moving from just calculus into more advanced aspects of it like Taylor's theorem, power series, sequences and all these, which now allows you to cross the boundary from calculus to real analysis. So, those who would love some mathematics at the end who should take note of these two weeks, because especially these things on Taylor's theorem and all, those who want can cross the boundary and go to real analysis. Thank you very much.